Hello, I'm going to start this video with a small confession. The derivations we are about to perform are perhaps a little pointless. The problem is that the next thing we have to do in this module is that we have to study the statistical mechanical basis for phase transitions. That is to say, we have to understand what happens to the particles in the system when a thermodynamic system undergoes a phase transition. In this video, you will learn why phase transitions represented a major problem for the developers of statistical mechanics, and why the work that resolved these problems was so celebrated. Having said that, however, we are not going to study the actual system which finally allowed physicists to understand the nature of phase transitions, the two-dimensional Ising model, as the mathematics required to derive the partition function for this model is well beyond the scope of this module. Instead, we are going to focus on the one-dimensional Ising model and show that this model behaves in a way that resembles how a system behaves when it undergoes a phase transition when it reaches 0 Kelvin. I am wary of calling this transition at 0 Kelvin a phase transition, however, as no system can be brought to 0 Kelvin in practice. To be clear then, the one-dimensional Ising model does not undergo a phase transition at any temperature above 0 Kelvin. Interesting things do happen to this system at 0 Kelvin, and we are going to study this behavior in order to come to some general conclusions about the nature of phase transitions. Before we get on to this business of the 1D Ising model, though, let's just briefly revise what we have learnt about phase transitions when we were studying classical thermodynamics. If you remember my previous videos on phase transitions, the final result we arrived at involved the Taylor series expansion of thermodynamic potentials. We said in that video that when a system undergoes a phase transition, some thermodynamic variable generally changes discontinuously. Furthermore, we also noted from classical thermodynamics that the thermodynamic variables were always related to the derivatives of some thermodynamic potential, and that as such, the thermodynamic potential must change non-analytically as one crosses a phase boundary. In other words, if in moving from S to S plus delta S, the system crosses a phase boundary, the thermodynamic potential cannot be calculated using the Taylor series shown here, as the derivatives, and hence the coefficients in this series, are equal to infinity. If you remember from the previous video, we introduced a classification of phase transitions. But this is not particularly important in this context. What it is important to understand is that the existence of phase transition implies that the thermodynamic potential cannot be expressed as an analytic function of the underlying thermodynamic variables. This realization about phase transitions is highly problematic for statistical mechanics. If you remember, the thermodynamic potential is related to the logarithm of the partition function. Hence, as shown at the top of this slide, the free energy is equal to minus kBt multiplied by the logarithm of the canonical partition function. Furthermore, the canonical partition function is simply the following sum over microstates. This is problematic as the exponential function is analytic for all values of beta, and because a finite sum of analytic functions is itself analytic, and because the logarithm is analytic on its domain. As such, the partition function should be an analytic function of beta and by extension of temperature. In conclusion, the statistical mechanics we have studied thus far predicts that the thermodynamic potential never changes in a non-analytic fashion, which is not consistent with the existence of phase transitions. As I indicated at the start of this video, realizations much like this one we've just gone through represented a great challenge in the early days of statistical mechanics. The problem was that the thermodynamic potential seemed to be analytic everywhere, and that as such there were no discontinuities and no phase transitions. In fact, there is no way of getting around this logic. Whenever you have a system containing a finite number of atoms, the number of microstates will be finite, and as such the thermodynamic potential will be an analytic function of the thermodynamic variables. Finite-sized systems do not undergo phase transitions. The solution to this dilemma comes when you recognize that the real systems that we want to study contain lots of atoms. So many atoms, in fact, that we can essentially assume that there are an infinite number of atoms. The fact that there are an infinite number of atoms ensures that the finite sum over microstates in the partition function becomes an infinite sum over microstates. And as we will see in the remainder of this video, if you take a sum of an infinite number of analytic functions, the function that emerges from the summation can change non-analytically. This brings us nicely to the first important point that I would like to make in this video. Classical thermodynamics only emerges from statistical mechanics when we consider systems with an infinite number of particles. This limit, the limit as we make the number of atoms in the system infinite, is known as the thermodynamic limit, and in this limit all the fluctuations in the thermodynamic quantities disappear. Questions will often ask you to calculate the value of some extensive thermodynamic quantity in the thermodynamic limit. Let's now consider what needs to be done when you encounter a question like this one. First of all, it is not asking you to calculate the total value of the extensive quantity for a system containing n particles. Such a request makes no sense, as remember that the value of an extensive thermodynamic variable will in general depend on the number of particles in the system. Hence, in a system containing an infinite number of particles, the value of any extensive variable will be infinite. When you are thus asked to calculate the value of the energy in the thermodynamic limit, what you are being asked to calculate is the average energy per site in the limit as n tends to infinity. In other words, what you are being asked to calculate is the value of the limit of e of n as n tends to infinity, over n as n tends to infinity, and where e of n is some function that tells one the energy of a system with n particles. Remember, we can get the energy as a function of n by taking minus the first derivative of the partition function with respect to beta as shown here. Let's make all this clearer by considering a simple example using our now well-known expression for the partition function of a system composed of n spins in a magnetic field. As we have seen elsewhere, we get the following expression for the average energy when we take the derivatives of this partition function. When this expression is inserted into our limit, the thermodynamic limit, we find that the n in the numerator and the denominator cancel out, and we thus have that the average energy per spin is equal to this relatively straightforward looking expression. This is all rather simple, but it does not answer our original questions about the nature of phase transitions. In this expression, E is an analytic function of beta, so we have admitted no discontinuities, and as would thus be expected, this model system thus undergoes no phase transitions at any temperature. To have phase transitions, we must have interactions between particles. It therefore stands to reason that we must look at the only system of interacting particles that we have examined thus far in this course, the Ising model. Remember from the previous video that the partition function for the Ising model could be written as the following sum of powers of the eigenvalues of the so-called transfer matrix. If you do not remember this, then it is probably worth revisiting the contents of that previous video. We did not use the expression of the rightmost equals sign in the previous video, but hopefully it is clear to you that this is a trivial rearrangement of the result that we did arrive at in the previous video. It turns out that this way of expressing the partition function is particularly useful when it comes to calculating thermodynamic limits because of a result known as the Perron-Frobenius theorem. This theorem tells us a number of enormously useful facts about square matrices with all positive real elements. In fact, we have already used one of the results in this theorem when considering the Ising model. We have used the fact that a square matrix with all positive elements, like our transfer matrix, is diagonalizable. We use this when decomposing the transfer matrix in terms of its eigenvalues and eigenvectors. In this video, we are going to use an additional fact from the Perron-Frobenius theorem, namely that any square matrix with all positive real elements has a unique largest eigenvalue. This is useful as it allows us to state with certainty that the quotient in the expression at the top of this slide tends to 0 as n tends to infinity. Think about this for a moment. If lambda 1 is greater than lambda 2, then lambda 2 divided by lambda 1 will be less than 1. As we take progressively greater and greater powers of a number that is less than 1, we get smaller and smaller numbers. It thus seems reasonable to suppose that this quotient goes to 0 as n goes to infinity. Let's now use this fact to calculate the value of the free energy for a group of Ising spins in the thermodynamic limit. Remember that the free energy is related to the partition function by the equation shown at the top of this slide, and that for a one-dimensional closed Ising model, the partition function is given by the expression shown in the middle of this slide. Inserting these two results into our expression for a thermodynamic quantity in the thermodynamic limit, we arrive at the expression shown here. We have seen, however, that thanks to the Perron-Frobenius theorem, lambda 2 over lambda 1 to the power n goes to 0 as n tends to infinity. As such, this whole second term in the expression goes to 0 in the limit. Meanwhile, in the first term, the n in the numerator and the denominator cancel. We are thus left with the following simple expression for the free energy in the thermodynamic limit. From the previous video on the Ising model, we know that the principal eigenvalue of the transfer matrix lambda 1 is given by the expression shown here. Before inserting this into our expression for the free energy of the thermodynamic limit, we will take a factor of e to the beta j outside the bracket as shown here. Taking the logarithm of this expression for lambda 1 and multiplying by minus kBt, we get the result for the free energy in the thermodynamic limit shown here. Take a moment and just pause the video to confirm to yourself that this is indeed the case. We now need to get back to this business of phase transitions. Remember that when a system crosses a phase boundary, the thermodynamic potential changes non-analytically, and that as such, one of the derivatives of the thermodynamic potential must diverge and shoot off to infinity, or minus infinity. We thus must demonstrate that one of the derivatives of the thermodynamic potential that we have just calculated is infinite at some particular value of beta. Showing that this is the case would prove that the system undergoes a phase transition. Before we get onto that proof, however, allow me first a brief digression. In this digression, I'm going to prove that this business of taking suitable derivatives of the logarithm of partition function is equivalent to the process of taking derivatives of the thermodynamic potential, a technique that we use to great effect when studying classical thermodynamics. Let's consider how we might calculate the average magnetization in statistical thermodynamics. We would take the derivative of the logarithm of the partition function with respect to beta h as shown here. Now suppose that we wanted the derivative of the logarithm of the partition function with respect to h at constant t. We could calculate this derivative using the chain rule as shown on the right here. Furthermore, because beta does not depend on h, the second derivative of this product is rather straightforwardly equal to beta. We can thus use what we learnt from this exercise to rewrite the magnetization, which we know is equal to the derivative of the logarithm of z with respect to beta h, as shown on the left here. Furthermore, we know that 1 over beta is equal to kBt, which we can insert here. and then that kBt log z is equal to minus the thermodynamic potential. We thus recovered the result that we might have used in classical thermodynamics, namely the magnetization is equal to minus the derivative of the thermodynamic potential with respect to h at constant t. We can now use this result and the result that we arrived at for the value of the thermodynamic potential in the thermodynamic limit to arrive an expression for the magnetization in the thermodynamic limit as shown here. Pause the video for a moment at this point and take the time to prove to yourself that this is indeed what you get when you take minus the derivative of our expression for the free energy in the thermodynamic limit with respect to h. Look now at the denominator in this expression and notice that if you take the quantity in the square root in this denominator outside of a bracket, what you get is equal to in the denominator is that square root multiplied by the term in brackets in the numerator. We can thus cancel these two terms and end up with the expression shown here. Pause the video again and just make sure that you're able to do this piece of mathematics. We can now continue on from this expression and arrive at an expression for the magnetic susceptibility in the thermodynamic limit by taking the derivative of it with respect to h once more. The result we arrive at is shown here. Pause the video for a moment and prove to yourself that this is the derivative you arrive at when you take the derivative of the expression at the top of this slide for the average magnetization in the thermodynamic limit with respect to h. The value of the susceptibility is shown plotted as a function of temperature in the graph on this slide. As you can see, the susceptibility is initially close to 0, then has a peak of around 2 or so before decaying away slowly. Further notice that this curve was calculated with the magnetic field strength H set equal to 0.99, as the shape of this curve changes as the value of H is changed, as shown in the video here. In particular, the peak in the susceptibility shifts leftwards and increases in height as h is brought progressively closer and closer to 0. In fact, it looks as if the susceptibility diverges when h equals 0, and that there must thus be something resembling a phase transition when h equals 0 and t equals 0. Let's confirm this to ourselves by setting h equal to 0 in our expression here. When h is set to 0, the expression simplifies considerably, as the hyperbolic sign in the second term is equal to 0 when h equals 0. We can thus neglect this whole second term. Meanwhile, in the first term, the hyperbolic cosine of beta h is equal to 1 when h equals 0, and the hyperbolic sign is equal to 0 when h equals 0. As such, we find that the susceptibility is simply equal to beta multiplied by e to the power 2 beta j. What is more, this function does indeed diverge as t tends to 0. When t tends to 0, beta tends towards infinity, and as such, the susceptibility tends towards infinity. To conclude then, I have shown that you can find points where the thermodynamic variable changes discontinuously, even though these thermodynamic variables can be expressed as derivatives of partition functions, and these partition functions are essentially summations of analytic functions. As such, we can reconcile the theory of statistical mechanics with the existence of phase transitions. As I stated at the outset of this video, however, the point we have found where the thermodynamic variables diverge is at 0 Kelvin, so this is not a real phase transition. A real phase transition would happen at a finite non-zero temperature. The mathematics required to study systems that exhibit real phase transitions is well beyond the scope of this course, however, and so this somewhat incomplete proof will have to do us for now. Having said all that, we have covered the two key points that I wanted to introduce in this video at length. We have discussed why phase transitions do not occur in finite-sized systems, and have argued that in order for a system to exhibit a phase transition, it must contain an infinite number of atoms. Furthermore, we have introduced the all-important notion of the thermodynamic limit and explained how we can calculate quantities such as the free energy per particle in systems with infinite number of particles. If you have understood these ideas, well done, and thank you for your attention.